Still a little slow. I have 7:30, so I think we'll go ahead and get this show on the road. So appreciate everybody, the brave souls who have decided to come. Again, what is this, session 8? So you've burned a lot of time here. I appreciate you coming. I know I've been picking on the models for, well, all 8 sessions, everything before this. So we're going to finally talk about them a little bit and hopefully encourage some intelligent use of these very interesting pieces of guidance information out there. So just to remind those online or anyone else that wonders where we are, this is the 8th of 9 sessions. Again, we'll talk about numerical models and followed up with some statistical approaches, information that can be derived from these model forecasting systems. And one thing I'll mention now with the forecast exercise, we'll talk about it at the very end. Again, the pattern itself is not the most conducive that you'll ever see for severe storms. So what I think we have tentatively agreed to do is to push the forecast exercise to the following week, so the last week of April. We'll announce with maybe 2-3 days lead time when we'll do that. We're going to hopefully look for a weather event because just next week looks like we would be wasting our time. It'd be about a 5-minute forecast if we're talking about tornadoes. So that's not real interesting given all the stuff we've talked about and not being able to use it. So we'll try during a dead week and see if we can squeeze something in one of those evenings. So we'll revisit that at the end. All right. Anytime we talk about models, this is the first thing I'm going to say is words of caution. I mean, because, this is where most forecasters go wrong, I think, is they jump headfirst into the model deep end and they don't really know how the models work. They don't really know how to use them, and they don't have the conceptual models in their mind to judge the model performance. So when you're using this information, first thing you have to consider, and it's a little bit ironic when I mention a week from now it doesn't look very good, predictability, it's pretty easy to demonstrate that after about day 5 or 6, predictability craters in numerical model land. Now, it's been getting better. Back when my career started, that fall off was at about day 3. We've pushed it out to day 5 to 6 now, but it still drops off dramatically. Point is, you get toward day 10, something like that, and your chances of the forecast looking like what it's shown in whatever modeling system it is not much better than randomly pulling a map out of a pile of 1,000 weather maps. It just means that there's not much correlation between the actual forecast and what really occurs. So I'm not going to spend a lot of time talking about trying to guess what next week is going to look like in terms of tornado potential because I think it's pointless. I mean, I've been doing this a while, and a lot of people waste a lot of time on that. We're not going to go there. We're going to talk mostly about short-term stuff. Again, and I'm not trying to insult the models when I say it's for entertainment value, but primarily, unless you are tasked with making a 1-week forecast of severe storms, that's all it is. It's just for the sake of amusement. Now, these model forecasts are really just estimates of the stuff we've been talking about. The synoptic regime, the sources for lapse rates, moisture, vertical shear, lift. All this stuff is what you're trying to get from the model forecast. You're not trying to let it decide for you. You're just trying to let, computers are really good at going through integrating equations forward in time. I can't sit down with a piece of paper and do this. However, what I can do is read between the lines. You have the conceptual models in your head. You can actually say something useful about the pattern, and you can actually come up with a better forecast than the explicit model would tell you. And again, as you get closer to event, observations, observations, observations. I mean, that's why I've been showing observations so much, and that's why we have waited till the very end to talk about the numerical models. And of course, what we will talk about a little bit here tonight is you got to understand what the models do to the information you're looking at. Here we have, most people look at forecast soundings now, and with the Python version of Sharp, you can, look at these to your heart's content. The point is, these are influenced very heavily by convective schemes in the model. You have to recognize when the schemes are active and what it is they do to the profiles, or you can easily misinterpret the information you get and come up with an erroneous forecast. All right, so what do they tell us? Numerical models, I mean, this might be just my way of viewing it, but the idea is you get the background synoptic regime and the sources and basic distribution of the ingredients. So you can track back, where's the air coming from in the mid-troposphere over, say, the Great Plains? Well, what's the lapse rate source region? We've talked about that. What do the lapse rates look like that? how do you move this air around? Low-level moisture trajectories. You can say something useful about that. Will it be a deepening cyclone? Do we expect cyclogenesis or not? Or in the case out here in the plains, lee cyclogenesis. Point is, you can say something intelligent about the background pattern and what that says about the distribution of ingredients. Now, the reason we've spent time developing these conceptual models is because that and the climatology is the only thing you have in your arsenal to judge these model forecasts. Again, unless you can sit down and integrate the primitive equations forward in time, and you can do this without error, which is something a numerical model can't do, you're really not going to beat the model at what it does. But what you can do is, remember, they're not forecasting tornadoes, hail, and wind, that sort of thing explicitly, so you're reading between the lines already. You can actually say something reasonably intelligent and not have perfect guidance from a numerical model. Okay, so what I'm going to talk about tonight, primarily the short range, the rapid update cycle, the RAP, the NAM, which is, the standard US model, and the GFS. Medium range, not really, but I've just listed some of the ones that are available, including the European model, the UK Met, Canadian GEM, and they all have ensemble systems that go with them, which we'll look a little bit at the short-term ensemble. And just at the very end, I will, just for fun, I'll show the CFS version 2 that gives you a forecast out to 6 weeks of stuff. And we'll show why we are potentially pushing the forecast exercise off a little bit. All right. I also want to focus on, I'm not going to show a whole bunch of SPC-specific graphics. I show a little bit, but most of it, I want to show things that you guys could look at. You don't have to barge into SPC ops and look at our one specific way of viewing a particular model. These are the 3 radar sites that I typically use, or model sites. The COD site has gone through a pretty major upgrade and overhaul over the last 6 to 12 months, and there's a lot of good information there. You can do time comparisons, model-to-model comparisons. There's all sorts of stuff and a lot of derived parameters. Twister data, that one, I kind of like the color schemes on a lot of the fills. Again, this is all just up to you, whichever one you want. And then if you've been looking at it as long as I have, you like to have a consistent source, and that's the UCAR site. And if you notice that the RAL, that is the correct identifier. They have an alias is what you normally see for the rap.ucar.e. So anyway, these are the 3 sites that I typically look at. I'll show a few graphics, mostly from the COD site in this talk. All right, there's basic stuff. We can go off in the weeds and talk for months about, hey, what model do you prefer? Which one does better? What about the 500 millibar anomaly correlation? You can talk about all sorts of stuff. I'm not here to argue specifically about which model's best, because I think it's difficult to say, because the performance characteristics of models are changing rapidly. But you can get base fields like 500 heights and wind speed, and you guys know this. I'm not telling you anything you don't know. Streamlines and dew points, I just grabbed a handful of fields. You can actually get direct forecasts of buoyancy, in this case, CAPE and convective inhibition. And this was for a not real exciting day. And even derived parameters like the supercell composite, or a version of it from the COD site. Convective precipitation, there's all kinds of stuff you can get from here. Some people love to just jump in and take it literally. The question is, how do you judge these forecasts if you're going to? Forecast soundings, I didn't exactly pick a real exciting one, so don't think, wow, where's that one? I don't even remember where it was, I just grabbed it. Some high base junk somewhere one of these days. The point is, you can look at this sort of information, you can grab on the fly at home, you can look at it on your smartphone, whatever. It's readily available, and it hasn't always been this way, but you can get all sorts of information on the fly. Now, how do you use these? That's what I want to talk about, is what do the models do? Again, we've got to look at predictability. When you're talking about a forecast, is this prog perfect? Or is there something that's liable to be wrong with it? So the idea here is that consistency of a model forecast tells you something about predictability. Now, that doesn't guarantee you, because it's consistent. It could be consistently wrong. There are biases in the modeling systems. But the point is, especially when you compare across modeling systems, consistency says something about predictability. More importantly is, if you have the conceptual models down cold, where hey, I know how the lapse rates form. I know where the EML comes from. I know how the moist layer evolves. then you can say something pretty powerful about what the thermodynamic profile should look like 2 or 3 days in advance, and you don't even have to use the model lapse rates and moisture. Or you can say, wait a minute, why do these look different than what I expect? And then, so the question is, without those conceptual models, you are completely at the mercy of the numerical model. And if you want to get good at forecasting severe storms, you're not going to get better until you start understanding being able to read between the lines, knowing what the lapse rates and the moisture and even simple stuff like that should look like. And again, looking at the synoptic evolution, this is going all the way back to like session 1, where we talked about cyclogenesis, we talk about QG theory and all that. What is it about this pattern? Is it assembling the ingredients in a way that favors severe storm development? And are there specific weaknesses in one or more of the ingredients, the moisture, the vertical shear, the lapse rate, sources for lift, that fit with the pattern that's being forecast? So you should be able to explain, why is there a cyclone in a particular place? Why is it deepening versus no, it's not deepening? Should I expect vertical shear to increase or decrease with time? This is all related to the synoptic conceptual models. If you understand those models, and again, if you're struggling with any of that, I encourage you to go back, try to go over the stuff we went over, and especially the first 3 sessions was the critical stuff for trying to judge the background model forecasts. Now here's the hard part. This is where I know people are going to ask, well, the models change over time, so it's really difficult to say anything consistent about model biases. What's the longest that any of these operational models have gone unchanged? Of the RAP, the GFS, and the NAM. Does anybody know? I didn't catch that.
I think it's NAM.
Yeah, the NAM, but how long? Couple of years was the guess. Try more like a couple of months. So they're generally updated multiple times per year. They can be changes to the convective schemes, the radiation scheme, the boundary layer stuff. It can be the assimilation cycle. Everything changes constantly. Because remember, there are paid professionals that are working on this. Just like you doing anything else. You don't get good grades because you don't do anything in class. You just sit there and smile. No, you actually have to turn in work. I don't get paid because I just look at pretty pictures on a computer screen but don't bother to put out a forecast. So some of this applies to the modelers. I mean, part of how they're judged is, are they improving the modeling systems, which unfortunately for the forecasters means, are they changing the system? So the biases may not be the same. The way the NAM behaved last year, and remember the NAM itself is not a specific model. It is a model slot on the supercomputer. It's actually the WRF model. And they can change the physics core with the model. And in the old days, it used to be the ADA model. That was a specific model type. The WRF is a specific type of model, numerical model. But the NAM is a slot. It can actually, the modeling system itself can change. So there is no real NAM model. There's a NAM model slot. So that makes it very difficult, to figure out how this is going to behave and to predict this year, I know based on how the model handled, say, the moisture last year, that doesn't necessarily mean that'll be the case this year. Okay, so I'll give you my general impressions. Again, this is just me. It may not agree with what you think you've seen, and, we could all be wrong. I could be wrong. Any and all are possible. With the NAM, I tend to pay attention to the moisture forecast. The NAM usually represents kind of an upper bound on the moisture return and even evapotranspirative influence. It tends to run moist. I think that's held through this spring. Again, there's a bunch of different reasons that could be the case. Another thing you may notice with the NAM is that it tends to have bigger errors, like with the synoptic waves compared to, say, the GFS or the European, as you get, especially in the out periods, day 2 into day 3. Well, part of that reason is that which model forecasts come out first? What's the first one that's available with every cycle? The NAM. The NAM is the first one. Well, the price for that is that it gets the worst initial conditions. It's basically rushed out the door so that we can have the first look. I mean, you notice by the time this talk is done, we'll already be getting some of the 0Z NAM. So we'll only be 2 hours after the nominal analysis time, and some of that will already be coming in. The price you pay for that is, they kind of rush it out the door, and it does not have as good a data assimilation cycle and initial conditions as, say, the European, where they take the opposite approach. They run the model 2 times a day, which is, counter to what most of the US modeling efforts are, but they try to get the best starting point they can. So there's a trade-off there, whereas, our version of it has been to run the models more frequently, but in this case, there are trade-offs. And then, of course, here recently, there have been some changes to the convective scheme in the NAM, and this is stuff that even makes it difficult for me, even though I look at this year after year. The performance of the forecast soundings. The structures are different looking this year than they were last year and previous years. And there's actually ongoing efforts to try to identify what some of the changes were the result of, and there's a parallel version of the NAM that's in development where they think they've maybe damped out some of this noise. But I'll show you a sequence of one of the soundings that illustrates it. GFS. Well, same kind of thing. It's been too cool and moist in the low levels for years. Now, there's been an upgrade this past fall that I believe looks like it may have toned that down some, so it appears to be a little bit more believable. And over the years, they've been trying to tone down the tendency for these crazy convective blobs, these explosions that you'll see where literally if you look close in the model, you'll see vertical velocity rings emanating out. That's like an overblown gravity wave signature. Crazy stuff in the adjustment going on, and it'll create these upscale growth of waves. I mean, you'll literally create something that looks like a shortwave trough out of a big convective explosion. That's fine when it happens, and it occasionally does, but not when you forecast it 10 times for every one time it happens. It just ends up making the forecast more difficult down the line for the person who's got to interpret this stuff. Again, it looks like the GFS has gotten better in that regard, so I think that I've been pretty hard on the GFS over the years. I think the system as a whole has been getting better, and it's certainly worth a look nowadays. All right, meat of this stuff is we're going to talk about the convective parameterizations and how to, at least my way of using the convection allowing models. So again, no more large scale. I don't care which model does better at, again, 500 millibar height anomaly correlations across the northern hemisphere. That's fine, but I'm not going to focus on that. That's pretty, esoteric stuff compared to a forecaster's not looking, hey, I can tell that this anomaly correlation really matters. You're not going to notice that in real time. Okay, so the convective parameterizations. Why do we have these in a model to begin with? Well, the primary reason is that if you have something like the NAM, you're sitting out at 12 kilometer grid spacing, which is what the native grid for the NAM runs are now, if I remember right. It's going to take an awful long time to saturate the profiles and to develop convection in the first place. So, and if you do manage to develop convection, you're going to have updrafts and downdrafts that are on a huge scale compared to what's actually observed. So the point is, at that broad a grid spacing, you can't effectively resolve thunderstorms. You just can't do it. So what we have to do is come up with a way to estimate the net effects of deep convection on the model grid. And it's sort of a two-way thing. Because again, anytime you change the temperature, moisture, and wind profiles, you're changing the balance in the model itself. So we've got to be able to, get this stuff to where the model doesn't go haywire, but you do come up with a realistic estimate of what the convection, how it's impacting the environment. The NAM model, which uses the BMJ scheme, so the Betz-Miller, this has been around for quite a while. It's one of the ones that, at least until this past year, I thought I had a pretty good handle on how it behaved. There's actually a shallow convective version. I'm not really going to talk about that much, but it's built in. It deals with shallow convection, and we're going to look mostly at deep convection. The GFS model uses the SAS scheme. This one is quite a bit more complicated in terms of what's included in it, and it is certainly a little more difficult to explain all the details of how it works. And in a similar manner, the Grell scheme looks an awful lot like the SAS scheme. So the RAP and the GFS are somewhat similar in their convective schemes, whereas the NAM runs one that's quite a bit different than those two. Okay, a convective scheme. These are the base processes that the scheme is trying to account for. We've got to start with convective initiation. You have to have a way to initiate storms. There's got to be something to trigger the scheme, so to speak. After that, we've got to actually represent the deep convection. Again, these are just the cartoonish estimates of it. And I mentioned shallow convection as well. So we have daytime heating and mixing, other shallow convective processes that are going on. You have to be able to handle the structures of the boundary layer. It's not just the radiation schemes. So there are other influencing factors, and the convective scheme tries to account for that. Now, the meat of it would be these bottom row here, where first of all, we're looking at if you remember what are thunderstorms trying to do? What's the basic reason that there's deep convection in the Earth's atmosphere? Redistribute heat and moisture. So we're trying to redistribute heat and moisture in the vertical. So that this first lower left box is essentially looking at the redistribution of heat. You have the largest latent heating is the loft. That's the biggest change. You have the largest rate of condensation down low, or the moisture content's higher. And then you're also you're basically redistributing that. So the scheme has to account for that in some way. We've got to account for the vertical redistribution of moisture. So we're looking at, you've got compensating motions in the convection. You've got to bring warm, moist air up and out, cold, dry air down and in. So we want to stabilize the profile. And then finally, on the ground, one of the biggest impacts of deep convection that we see is precipitation. So you've got to actually have that included in the convective scheme. So remember, these are processes occurring on the smaller than the grid scale, so we've got to somehow get this into the model and keep everything in balance. All right, so the NAM BMJ scheme, what does it do? So if you want to trigger the BMJ scheme, and if none of you have seen this before, this is stuff to keep in mind when you're looking at the forecast soundings. We need CAPE through a 200 millibar layer or deeper. And it's not a whole bunch of CAPE. So we just need buoyancy through some layer of some reasonable depth. The one you may not know is that it's highly sensitive to mid-level relative humidity. So and when we talk about this scheme, this is actually designed after tropical convection is where the work was done for the BMJ scheme. It's not like plains, loaded gun, continental environments. This is looking at tropical convection, what the environment looks like before and after, and that's how this scheme works. It tries to leave an atmospheric profile after the convective scheme is triggered that looks like the post-tropical convective profile, which in a general sense is doing the same thing as continental convection, but they're usually different lapse rate environments. So again, keep in mind, you need some buoyancy and you need sufficiently high relative humidity in the mid-levels to get the scheme to trigger. And again, once it's triggered, there are these tropical reference profiles, and I'll show you kind of what they look like. So what it does is it says, okay, if the conditions are met, the scheme triggers, it tries to force the environment on the grid scale back to these reference profiles. Now the neat thing about this, or what's funny is you might look at this and say, how does this thing work at all out here? You might wonder, it's the mid-level relative humidity. It doesn't care about convective inhibition. It doesn't have downdrafts. It's like, how on earth does this scheme work? Well, when we look at the strengths and weaknesses, where does the environment tend to moisten in the mid-troposphere? It's where ascent is going on. If there's something forcing the ascent, that means you've got something organized going on the subsynoptic or synoptic scale to condition the environment. Go all the way back to sources of lift. That's exactly where thunderstorms tend to form, is areas where the larger scale pattern has conditioned the environment down to where mesoscale processes can initiate storms. That's what this scheme actually represents. In sort of a backhanded way, it gets at the idea, if it's moistening through a deep layer of the troposphere, chances are there has to be ascent associated with that. But not in every circumstance. For this reason, it works really well with elevated convection compared to the other schemes. And also, there are some trade-offs. Now, again, it's a little tricky with the way it's changed. They tried to get it to tone down the warm season convection and made some tweaks. I don't know if they went too far because they're working on tweaks to sort of undo some of the recent tweaks. So we haven't really had a chance to look at it too much. But the idea is that we can find cases in the not too distant past where the scheme, take our standard loaded gun sounding. You've got real steep lapse rates, moist boundary layer, but a big cap sitting on top of the boundary layer. Occasionally, you've probably seen these cases here where you get the subtropical cirrus plume, and you'll see virga, fall streaks, and occasionally sprinkles at the ground, but it's all stuff way aloft. The Betz-Miller scheme would occasionally trigger because it would get just moist enough with the falling precipitation from aloft, or just moisture convection from some other source. It gets just over the relative humidity threshold, and the scheme triggers. Remember, it doesn't care that there's inhibition. It just knows, hey, I've got CAPE, it's moist, bang. And then it completely changes the profiles, and usually you'd see these really erratic convective precip signals that would go up and they'd wander off in directions, like 90 degrees off from the base flow. It wouldn't make much sense when you looked at it. You'd say, why? But you would also have to think, because you're saying, wow, I've got 3,000 or 4,000 CAPE environment and 50-knot shear type profiles. If it goes, it's a supercell environment. So this makes life for the forecaster very difficult, because if you do get storms and you're the one that said, I'm going no thunder, and then someone can point back to the convective and say, well, there was convective precip all over the place. What are you talking about? Those are the kind of things you fight in forecast land. Conversely, you can have occasionally some very interesting looking profiles that are not capped, moist, large CAPE, but it's dry in the mid-levels, reflective of the EML source region. And the scheme will not trigger. Because remember, it doesn't care about mass flux. It's not thinking of it in the standard sense that you have forced low-level ascent, and you moisten and deepen the moist layer from below, you erode inhibition, and then an updraft initiates. It doesn't work in that way. So if you don't have the background moistening in the mid-levels, it doesn't care what the profile looks like. All right, so we're going to show this is from the Moore day. This is a sequence of soundings from the, and this shows the BMJ scheme kicking in. There might even be some influence right there around 850 in the sounding, because that's not a very realistic profile there. But what I'll do is we'll step through this one and show, or this actually isn't, sorry, I jumped ahead of myself. This is down by Houston. I'll show all three models, and then we'll show the entertaining one for here. So this is what the Betz-Miller scheme does. Convective case down somewhere on the upper Texas coast. You notice this characteristic moistening with time, and then see this big vertical velocity response? That's a sign that the convective scheme is acting. This is just a 1 hour change. This isn't like, oh, well, the big synoptic wave arrived. No, we finally moistened enough, and that's a sign of the mass adjustment related to the scheme. And then once the convection is done, notice these relatively smooth temperature and moisture profiles. We've reduced some of the convective available potential energy, and you've got these kind of smoothed out. So if we sort of step back through those, you see the smoothing, moistening, trigger, blow up, and then kind of this relatively smooth profile. So that's pretty characteristic of the BMJ scheme. Okay, let's talk about the GFS, the SAS scheme. This one, as I mentioned, it's much more complex than the BMJ scheme. It's got entrainment, detrainment, compensating vertical motion. It looks a lot more like that 6-panel schematic I showed. And in this case, here's the things you have to keep in mind is what triggers the scheme. So you need CAPE rooted near the ground. But I think what's important on this one is there has to be local destabilization with time. Well, what scenario can you think of that might pose a problem? It's common out here. Can anyone think of a scenario where it's not constantly moistening and destabilizing with time? That sounds like the north edge of a warm sector, maybe warm frontal type stuff up near areas where there's lots of large-scale changes going on. What about south of a surface low in the plains? What's there? What do we typically find? Dry line, yeah. So it's the dry line case. Well, you don't necessarily see the time rate of destabilization. You can diurnally, but you don't always achieve this condition locally, so it can be difficult for this scheme to trigger. And the same kind of thing applies to the wrap. So it could be, whereas the BMJ scheme, if you don't have background ascent and moistening in the EML layer, you won't see it trigger. In this one, if you don't see the low-level changes in static stability, then it may not trigger. And again, this one doesn't alter the temperature and moisture profiles nearly as dramatically as the NAM does. Now, it occasionally, I'm not even sure of all the reasons why it creates the grid scale bombs, but anyone who looks at the GFS, fortunately, they're becoming less common. And again, it doesn't stabilize things as much as it should. All right, so here's the same Houston area soundings, same convective scenario. This is the kind of change you see in the GFS for the same, because they were all active. All the convective schemes were active in this case. So you do see a vertical velocity response, but you don't see quite the wholesale changes. There's a little bit of moistening aloft, but you notice the lapse rates aren't altered dramatically anywhere, and it doesn't strongly stabilize any part of the profile. So this is pretty characteristic of how the GFS would respond. All right, Grell scheme, which is, again, similar to the SAS scheme. Again, this mass flux in the low levels that's required is going to be sometimes what I think is keeping it from triggering. But this has explicit downdrafts and can develop cold pools for the right reason. Has anyone ever seen NAM profiles where it looks an awful lot like there's a cold pool there in the pressure field or something? I mean, have you seen that where it looks like a meso-high and there's a big precip blob in the NAM? You might have any ideas why you might get what looks like a meso-high from a scheme that doesn't produce downdrafts? How can you do that? Any guesses? I mean, it's not a trick question, but it's a little bit tricky. What other schemes are running actively in the model? What other processes have to be parameterized? Microphysics would be one that's mentioned. There's another big one that we haven't, I mean, I've mentioned it, but I haven't heard it here. What would be another scheme? The radiation scheme. So the key here is when you trigger the scheme and in a parameterized sense you create thick clouds, that alters the radiation budget at the surface, and you can actually create a cooler blob because of changes in the radiation budget and also the microphysical influences. So kind of an indirect way you can create things that look like cold pools, even though it doesn't actually create cold downdrafts that spread out beneath the convection. All right, so here's the Grell scheme. Again, these aren't meant to represent the way every single case would respond, but the idea here is for the same exact location, convective scheme's active in all these. You notice the Grell scheme, again, it doesn't do much to the lapse rates aloft. There's some deepening of the moist layer, but you don't see the complete overhaul of the profile that the NAM does when the scheme's fully active. So again, the GFS and RAP soundings are going to look a little more similar in the locations of convection to what they did pre-storm, whereas the NAM will often make huge changes. Now, I do want to show that the feedback's not unique to the GFS. You can get some pretty amusing stuff when you have, usually it's related to large buoyancy, but here's one from the BMJ, and when I mentioned the Moore case, this was the case with the tornado back on March 25th, I think it was. I'm going to go through the sequence of NAM soundings, and we'll look at how they change when the scheme leading up to convection, and then what happens when the scheme triggers. So this is starting at midday, 18Z, we got a shallow moist layer, and this is a case where we have heating and mixing. Now, thinking back to when we talked about the evolution of the moist layer, is there anything in there that might look a little unusual that you would think would be at processes that would be at odds with one another? So we have heating and mixing, the boundary layer is getting deeper. What's happening to the moisture at that same time?
Increasing.
So if the moisture is indeed increasing, how would you get increasing moisture at the same time that the boundary layer depth is increasing? Which should be mixing dry air aloft down into the boundary layer. It should be the opposite. How would you get increasing moisture in the face of mixing? So there has to be lots of moisture evacuation. What's the other possibility? Wouldn't have been as likely in late March, but might apply a little bit more right now. What's happened since late March here? The wheat, it's evapotranspiration, so we've greened up. The soil's moist and we've greened up. So it would be a little bit more of an influence now, but there's got to be either a local moisture source or there's got to be offsetting advection. In this particular case, when you look at the soundings, would you characterize this as an environment with very strong horizontal moisture advection? Just look at the wind profiles down low. I mean, the depth of the boundary layer and the strength of the wind profiles. It's not that strong. So this isn't one where you would expect massive horizontal transport of moisture, say with this huge source region in Texas. The boundary layer looked pretty similar down all the way to Fort Worth. So the point here is when you see these kind of things, you might immediately think, wait a minute, I see increasing mean mixing ratios in the face of heating and mixing. If it's not a strong moisture advection scenario or with big upstream moisture gradients or there's not huge local moisture source, you might immediately question that and say, wait a minute, this has nothing to do with the convective scheme. You might say the background environment perhaps is not going to look quite this juicy. All right, so we keep going on here, and now there may be some, I didn't talk about the shallow scheme, but if you look around 850, there's sort of it looks like it saturates, and then you see the moisture sort of creeping up, and it's right there where we've eroded whatever little cap is left. That might be a response to the shallow convective scheme. That's one of the things that it's been known to do. But at this point, we don't have storms, and the only influence you have here is you notice there's some subsidence, the blue arrows, anything that's blue would be downward vertical velocities through much of the mid-troposphere. What I suspect has happened is the convective scheme is going somewhere very nearby at this point, but it hasn't affected too much this grid point. But we go to the next hour, and you start to see, notice the huge change in the moisture profile. Suddenly it's moistened, almost unrealistically saturates, which you could argue that's close to a MAL, a moist, absolute, unstable layer. You know, dry adiabatic or steeper and saturated is almost impossible to maintain. But we've got that very big velocity, vertical velocity spike that shows up. Now the entire sounding's completely saturated. We still have the Cape. And, you know, this is an explosion. Those vertical velocities are greater than a meter per second, which is nowhere close to large-scale ascent. This is something down more on the updraft, mesoscale type stuff. Now you notice we finally get rid of some of the inhibition, or some of the Cape is, and we've completely adjusted all the profiles. Now they're starting to get that smooth look and still have huge vertical velocity, but also look at the model wind profile. Does that look realistic? Look how smooth that is compared to what the profile looked like pre-convection. This is clearly a response to the background model fields to this blow up in the convective scheme. This is a form of feedback. Oh yeah, it gives you this nice big loopy hodograph, but if you were to just, how would you interpret this profile if you don't know this is the convective scheme? What do you think's gonna happen there? I don't even know what you would say is supposed to happen. Well, it's saturated in the lowest 200 or lowest 800 millibars of the profile. We have 2,000 Cape. We've got a semicircle hodograph that looks oddly, I don't know how you would interpret what this is supposed to be, but chances are it's not really going to look like that. You would have to develop some sort of tremendous convective feedback, and you'd see that in the observations, a giant MCV or something would start to form if this is really occurring. So point here is that it has a dramatic influence on the profiles, because remember, this is right before the storm started. It might be a little too moist, maybe the Cape's too big. We'll look at that. And it's sort of a run-of-the-mill supercell profile in terms of the hodograph. And we've completely changed everything. So let's look at the forecast since we talked about the moisture. This is that NAM forecast valid at 0Z for Norman, which is close by on the storms. Here's the observed sounding. So remember, we suspected something might be goofball with the moisture, and indeed the observed profile suggests that it's a deeper mixed boundary layer, so it's a little bit warmer, but the moisture is not as well mixed. And again, it's, you know, I don't know, we can't be sure that all the details are correct. I don't know which sensor Norman's using, if it's the old Sipicon thing. I don't think so. So as best we can tell, this is a reasonable depiction of the environment. But, you know, there are noticeable differences. I mean, in terms of, if you look at LCL heights and things like that, maybe the vertical shear isn't worse, but certainly it's a little bit drier, warmer environment. Still fairly unstable. All right. That's essentially what I'm going to say about the convective schemes. I think the important thing is just to look at them and know that they're there and that they have a serious influence. All right, now we'll talk about the convection allowing models and, you know, hopefully get you to maybe consider avoiding some of the pitfalls with these things. So when we talk about a convection allowing model, we're saying they don't need a convective parameterization scheme. The grid spacing's small enough that you can actually create updrafts and downdrafts on an appropriate scale. Usually this is down somewhere around 4 or 5 kilometer grid spacing, and they can handle most of the convective processes. However, there are still parameterizations in even these convection allowing models. There are still radiation schemes, there's still microphysics schemes, there's still boundary layer flex schemes. So the interaction with the air in the land or the air in the sea, the interaction between precipitation particles and the background environment, all that stuff is still parameterized. They all have different tendencies that result in different structures. And you can see influences on what the moisture profiles look like just from these boundary layer schemes. I know Ariel's done some work on that in the cool season, but it's remarkable how much difference the background schemes make that have nothing to do with deep convection. All right. Here's the tantalizing part. You can get, oh, I got this radar-looking thing. Boy, we've post-processed this, and I get stuff that looks like radar reflectivity. I mean, we color-code it to make it look just like a radar image. I get characteristic supercell shapes. Wow, I get, this has got to be right because it looks so realistic. Well, if you're, first of all, they'll be consistent with themselves. That's all you can say about the model forecast is it will be internally consistent, but it can be completely wrong. And the only way you're going to be able to say something about it is if you have a background expectation, which is necessarily going to be rooted in the larger scales. So you're going to have to look at the distribution, the ingredients, sources for lift, what sort of convective mode you might expect. And again, probably the best way to use these is to develop a forecast yourself, use this information to help confirm your suspicions or to point you in a better direction. If you see something that you didn't expect, then go back and try to explain, what am I missing? Sometimes you're not missing anything and the forecast is wrong. Other times it can be, wait a minute, this might actually be pointing me in the right direction. Okay, so what does this typical grid spacing look like? This is the Valonia Mayflower supercell from late last April over near Little Rock. I've just put in a series of grid points. These are at 4 kilometer spacing, and we're focused on the mesocyclone region of, this is a large supercell. You can see there's only a handful of grid points to resolve the entire mesocyclone structure, the rear flank downdraft, and part of the forward flank of the supercell. Do you think that's sufficient to fully represent a supercell storm? I see a lot of head shaking. Yeah, and you're right. That is a very crude representation. This might be more akin to, before most of your times, like the old LFM model, where you'd have 200 kilometer grid spacing, and you could sort of resolve large-scale synoptic waves. That was about it. You know, the old rule is like a 5 delta. You can't resolve anything that isn't at least 4 or 5 delta x. So 4 or 5 times the grid spacing or the wavelength of the waves you can resolve. So in that case, you could get the big scale troughs right, but any details were complete gibberish in terms of the model. So in this case, something on the scale of a tornado. How many 4 kilometer wide tornadoes have you guys seen? Now, you might have seen one. I am aware of one that was kind of like that, but you might have almost been in it, unfortunately, and I'm not going to comment any further. But the point is, even if it's nearly that grid spacing, you would resolve the tornado with what, 1 grid point? That's completely insufficient. You might need, the only things we have now in numerical modeling world that look like they resolve supercells, if you've seen the Lee-Orff, that simulation of the Piedmont storm, which is pretty interesting, I think that's down at 20 or 30 meter grid spacing. 20 or 30 meters, so it's 30? Yeah, so I mean 30 meter spacing. This is 4,000 meter spacing. So there are obviously a lot more grid points to try to resolve something. And that's just barely what you can do for a tornado. You're just now getting to where you can resolve a big tornado. Small tornadoes, I've seen tornadoes that were smaller than 30 meters across the whole debris field. So again, you just have to consider what can the model represent. So there's a ton of details. There are crude structures, these loose kidney bean things, maybe some semblance of a rear flank gust front, and a rotating updraft. Now we can tell that from one of the derived parameters that we look at, which would be the updraft helicity. You know, I don't know if you knew how this is calculated, you're gonna know now. So it's just the integral of updraft and vertical vorticity. So basically where the air is rising strongly and spinning cyclonically, that's updraft helicity. And it can be positive or negative. In this case, the spin's cyclonic or anticyclonic, and it'll give you positive or negative values. So that is a direct indication of a supercell type storm. If you have a strongly rotating updraft, the rotation is co-located with the updraft, and this integral is large, that's going to tell you that indeed it could be a supercell storm. Now in the example I'll show in a minute, the purple shaded hatched area, that represents the updraft helicity greater than 25 meters square per second square. So that would be the rotating updrafts. Not even close to resolving tornadoes. Think back to session 4, the supercell conceptual model. The closest that we get with this is like some estimate of the mid-level pressure perturbation. So you've got like how strongly rotating is the storm, how strong will that suck factor be? It doesn't necessarily tell you how close to the ground. It depends on what layer you integrate for updraft helicity. But it gives you some indication if it's spinning strongly in the mid-troposphere, it may strongly draw you in down on the low levels. The low-level updraft could be stronger. That's more favorable for tornadogenesis because the stretching term's stronger. But again, you've got to make a bunch of leaps there to connect the dots from large UH down to tornado. So again, it's not explicitly resolving tornadoes, just strongly rotating storms in the mid-troposphere. Okay, we'll look at some of the cams that at least I'm familiar with and I look at regularly. This is one, the Nestle Wharf ARW core. This one runs twice a day. It's at 0 and 12Z, 4 kilometer grid spacing and horizontal. It's just what we call a cold start, and from the NAM initial conditions. So basically whatever the initial conditions for the NAM are just fed straight into the Nestle ARW, and it goes. And of course, you know that you got to be careful with that kind of thing in the first few hours of the model forecast, because again, it's starting a cold start. And you know, probably the most important thing about this model, though, is that, like I mentioned, a lot of these models have been changing rapidly. The Nestle folks here in the building have worked with us at SBC directly, and I'll give them credit for running the idea by us, should we make changes to the Wharf core? They wanted to, you know, because someone's constantly updating this stuff. They needed to make some of the updates for computer purposes, but they wanted to see, should we keep the base core of the model the same? And what they did is they were kind enough to do some reruns of historical cases for us, and we looked at the performance. It turns out the performance with the new core was not really any better than the old core. So what they did is, for our benefit, they stayed with the old formulation of the model so that it would be consistent over multiple years. So this goes all the way back to the late 2000s. It's been running essentially the same. So in this case, it's not a moving target like all the other models so much. It really is something where you can look at its tendencies and say something useful about it. And so I've got the web address up there. You could just Google the Nestle Wharf and probably find it as well. All right. They give you all sorts of neat structures, and here you go. Here's a forecast. Now this one is from the SPC system, so I apologize. It's the only one I'll show that's unique to us. You see the characteristic kidney bean echo shapes. You notice the shaded purple. It's right there in that inflection, what looks like the inflow notch. There's a rotating updraft sitting atop that. It looks like classic supercell structure, and there's several of them in southeast Oklahoma. Now those of you looking, and this isn't too far back, you might think, okay, how many days have there been a swarm of supercells in southeast Oklahoma? If you're having trouble remembering one, that might give you a hint how this whole thing turned out. Okay, these are the updraft helicity. You see these little swaths. These aren't terribly strong. That one that's closer to Broken Bow Reservoir there in McCurtain County or whatever, that one, I mean, those are modestly strong updraft helicity values. This isn't anything that's like super high. And again, you have to keep in mind when you look at UH, you can't really compare easily model to model because this is resolution dependent. So really you can only compare Nestle ARW updraft helicities to Nestle ARW, same formulation. You don't want to compare this directly to the HER, for example. Okay, well here's the verifying radar image and background cape and vertical shear at the time of that forecast. I don't see the swarm of supercells. You might go, wow, that's not real helpful as a forecast. And I'm not trying to pick on the Nestle Wharf. It's as good as any of the other cams out there. But a pretty picture does not make a right forecast. So the question is, what happened in this case? And it's the same kind of thing that happens to chase days and everything else. Messy, real-world storms formed that weren't forecast, and they completely butchered the environment. And you'll see in this case, I know we talked about this last week a little bit with some of the preceding convection, how it might influence last Wednesday's event in Oklahoma and Kansas. And you notice it kept everything cool. And some of the influence last week was there was a supercell in northwest Oklahoma. Looked good, moved into the cool air remaining from where it was cloudy and it had light rain all afternoon. Convective inhibition killed it. You take away all the light rain and the clouds, I doubt that scenario turns out that way. Okay, and then we also have the influence of the storms. In this case, there's a whole MCS forms and overturns the entire environment before that forecast time. So when you look at this, there's the actual forecast, valid around midnight or so. You see a little bit of convection northeast Oklahoma in the Nestle forecast. Again, this is using the NAM initial conditions, but what's this whole band of storms that comes back to Norman? And just to prove they were here, there were some nifty pictures. Nice laminar cloud structures and forced descent. And this is coming in over there off Highway 9 or whatever. And so the idea is there were storms where there weren't supposed to be any. Well, what did this look like about 6 hours later? It's a big MCS. You see the lightning is that arc of the little, those are all the cloud to ground strikes, very cold tops. It's a typical well-structured MCS. Where did that cross in the previous few hours? It went right through the area that's supposed to have the swarm of supercells right around this time. Instead, there's an MCS moving into East Texas. So we'll look at the sounding. Here's what the radar looked like at the same time. We'll do a sounding at Paris, Texas, which should have been the inflow side to the swarm of supercells. Here's what the sounding was forecast to look like in the WRF ARW. Fairly large cape. It's rooted the most unstable parcel slightly above the ground. Typical supercell type profile. Okay, everything looks fine. Maybe the storms might behave as they were slightly elevated. Here's what the forecast sounding looked like once we had the influence of the MCS in there. This is still a forecast, but now it's actually reduced all the cape. And you go from one where you say severe storms to I don't think there'll even be a thunderstorm after the profile's been stabilized. So this is a case where you can have all the fancy detail you want, but if you don't know that MCS is going to be there, this particular CAM forecast wasn't going to help you. And that is a common problem. All right. The HER, which is probably the flavor of the month, I mean, it's actually a pretty interesting modeling system. This one updates much more frequently than the others, every 15 to 60 minutes. Most of us probably look at the hourly output. This is on 3 kilometer horizontal grid spacing, so it's a little bit higher resolution than the Nestle WRF and a lot of the other CAMs. And this one's a so-called hot start. We include radar data. This one is constantly cycling on itself. So, it's kind of, essentially they try to give it a running start, and it runs every hour, and it goes out far enough to where it just keeps doing this for itself. So it's a difference in the data assimilation cycle compared to the Nestle WRF. And of course, there are a lot more resources devoted to this one. The Nestle WRF is kind of done in-house and out of hide. This is done at a modeling center. So there's a lot more horsepower devoted to running this system than just say something like the Nestle WRF. And you can run some of these yourself, maybe not the CAMs very effectively, but some of the other workstation versions of these models. Okay, I want to look at a HER forecast that sort of illustrates the good and the bad of its ability to help you forecast convection explicitly. So this is one, we're going to step through, many, many hours. This would be the equivalent of you wake up early morning on a chase day. And the first run of the HER that you can look at might be the 9Z run or something like that. Now, you're getting up pretty early and you're going to look at this religiously all day long. Some of you may not see it until the halfway through my loop when you finally get off your lazy butt. Someone in the back, that I won't mention, Ben. Anyway, we're going to just keep in mind, don't focus too much on the details, but again, watch the evolution of the storms, and we're going to focus on the Texas Panhandle. So this is a convective event out there. This is the forecast 15 hours out. Now they go every hour. Just look at the change in the echoes. These are hourly. So you notice here we had sort of a decrease in the convection for a few hours. We're 12 hours out now. It looks like everything's going away at 0Z. Oh, wait a minute. Storms are coming back. Now there's a bunch of storms. And now we're left with the 5-hour forecast. So I'd stop there because at this point, this is probably, if you're going to go out and look at these coming from any distance, this is one of the last things you'd see before you have to make a decision. Because remember, they're delayed by an hour or two, and this is a few hours out. So the idea is we've got sort of a mixed signal. We have storms, we don't have storms, we do have storms, and they're kind of scattered around the panhandle. Okay, let's jump to a later time, 2Z. Just 2 hours later, same kind of forecast. Early forecasts had storms. They're going. In this case, they don't completely go away like they did earlier, so maybe initiation in this model forecast was delayed a little bit was the main change. But if you look at where they are, there are not too many of these that are in the same place. The idea that you're going to, hey, I see this perfect supercell and I'm going to go to this county exactly at this time. That actually occasionally works. There was the Panhandle, the most recent event in the Texas Panhandle, southeast Colorado, southwest Kansas, was a pretty remarkable forecast where that worked. However, the only reason it's believed is because the observed data supported it well before the storms formed. So we look here, this is 2Z. So you can see sort of the change in this one over time. So the question is, how do you use this information? And again, I'm not telling you something you probably don't know if you've been looking at it. But the idea is you have to consider how consistent is this in terms of the kinds of storms and where they are, and does it fit my background expectation? Should I expect storms to be here in the first place? Okay, here's the updraft helicity. I'm just going to look every 3 hours. What kind of storms are these? So we're looking for rotating storms with updraft helicity signatures. You see them, they're Amarillo, then they're weaker, then they kind of come back. And then the 2Z forecast, same kind of thing. They're bouncing around a little bit, but you keep getting some kind of signal for rotating storms. So this tells you that in Model N, this is a favorable environment for rotating storms. It's not necessarily sure where the storms are going to be exactly. So the point is you would have to, in your forecast, you would have to build in some leeway. You can't just say, I'm going to circle Shamrock, and that'll be right, or I'm going to circle Canadian, or something like that. Okay, so the summary in this one, there's some variability in the timing of the specific storms, and you can't really find the same one very easily run to run. However, there were storms in most of the forecasts. So what we did here was we did what we call a time-lagged ensemble. Poor man's version of it. We looked at a whole sequence of model runs valid at the same time and look at the time trends as a way to get predictability out of a single model. That's one way to do it. Same thing you do if, like, I look at the GFS today and then I look at tomorrow, do I see the same features that I saw yesterday? Again, you want consistency, but you have to have an expectation. Do I expect thunderstorms to form here? Does it look like it should be a supercell environment? You're going to have to do that work yourself. Here's the observed sounding from Amarillo that evening. So this is right around supposed go time. Does it look like there's any potential for supercells based on this one? I see a pretty deep mixed boundary there, sufficient moisture, moderately unstable. You know, it's 2,000-ish, 1,500 ml CAPE, and a fairly characteristic supercell hodograph. Not tremendous low-level shear, but it's a somewhat straight hodograph, but plenty of deep layer shear. There's a lot of length to the hodograph. So the background environment looks favorable for supercells. And indeed, we did get one meaty supercell, just east of Amarillo. Now, the HRRR never actually showed that storm. It had storms east of there, southeast of there, north of there, northwest of there. It was kind of all around it. This is where it ended up. But the idea is the HRRR would definitely get you in the ballpark within several county radius. But that's all you can really expect them to do in most cases. All right, we have a new one. I just found out about this one today, actually. So I can't really tell you anything about the performance characteristics or whatever else, but it's interesting because it's a 10-member cam ensemble. This is run at 3 kilometer resolution. I gave you the full-blown web address. Apparently they're going to change within 2 weeks to the new alias, which will be the ensemble.ucar.edu. So you guys can use that, and it's actually, I'll show you just a screen capture of the interface. It looked pretty neat to me. I mean, because it's got a lot of ensemble-based stuff, so you can look at model spread, you can look at ways to get at predictability, and how much variability is there in the forecast. And that's never a bad thing to have some estimates, quantitative estimates of predictability. So this is just what the interface looks like. It'll probably be a lot worse for me using this at home because I have pretty sorry bandwidth, but here with a fast connection, it worked great. So if you have, plenty of bandwidth, then it's real easy. It works kind of like a lot of the others. You mouse over the forecast hours. You can change. There are some subdomains that I'm just looking at the whole CONUS. This is just a CAPE and 0 to 6 shear forecast. It actually has a few parameters, derived things like the significant tornado parameter, and there's lots of stuff in here. I just encourage you to go explore it because it's really just now being released. But it looks like it's another tool to add to your arsenal. Okay, so we'll summarize this. The numerical models, before we take about a 5-minute break, is we've got the RAP, NAM, GFS are all reliant on convective schemes, and they have different requirements to trigger the schemes. So, if you want to say anything intelligent about how the environment's responding, you have to know how the schemes behave. And then, of course, you've got convection allowing models that don't rely on those schemes, but still have lots of other parameterizations in them necessarily. You can get all sorts of neat fields, simulated reflectivity. You can see if there's updraft helicity. Is it a rotating updraft? But again, I want to emphasize rotating updraft does not equal tornado. You hear claims all the time. Our model showed this 12 hours in advance. It did not. There are very few models that have ever in the history of the world shown a tornado in advance because almost none of them have been able to resolve them. And there's almost no computing systems that can handle the computational requirements to run that, and certainly not in real time. That's going to be a while. So again, keep in mind what they tell you realistically, and you're going to use your meteorological analysis skills and your understanding of the conceptual models to fill in the gaps. So that's what I got for the base numerical models. We'll take a few-minute break here, let's just say 5 minutes, and give you a chance to stretch or not have to listen to me. And then we'll come back and I'll show some statistical post-process stuff that's available that are other ways to milk information from these forecast systems. So again, we'll take a few-minute break and then we'll resume here in about 5 minutes. All right, so we'll talk, this will kind of be the home stretch of the numerical model discussion, and it's actually kind of the home stretch of the regular presentations. As I mentioned, this is the last of the more workshop class kind of like stuff. It'll be more interactive if we can do the forecast exercise the last week. Okay, so there are some statistical approaches that are available out there. You know, some of you may be very familiar with these. If you're not, this will be a good chance to see what's available. This is kind of stuff that we look at SPC pretty regularly. We have the SREF, which is the short-range ensemble forecasts, and we have all sorts of probabilistic guidance and different ways you can use an ensemble there. We have the SSEO, which is the storm scale ensemble of opportunity. So the SREF is actually more of the mesoscale model ensemble. The SSEO is what I'd call the poor man's version of an ensemble of opportunity, taking the actual independent cam-runs that are available, and we just sort of mush them together to make an informal ensemble. And then, of course, we have some derived stuff from the Nestle ARW, which tries to give us estimates of things like what probability distributions would look like in the sense of a SPC probability forecast. Okay, so the short-range ensemble, this one's actually a 22-member ensemble, and we have all this stuff is on the SPC website. Those are the graphics I'll be showing. It's readily available. There's 7 different variations in initial conditions and model physics of 3 different models, plus we have a NAM control run, which is if you look at the SREF times, those run at the off synoptic times, 9Z, 15, 21, and 3. They use 1 time lag NAM. So there's the NAM forecast explicitly from 3 hours prior to the nominal time of the short-range ensemble run is included as the so-called control run. So again, we vary the model physics, we vary some of the aspects of the convective scheme and the initial conditions. The idea being if you throw enough little tweaks in there and you run the forecasts forward, the idea is how predictable is this regime? Are small changes resulting in big changes down the road, or is it relatively resilient forecast such that these small changes don't grow over time and don't make a big difference to the later forecast outcome? Okay, that's what you hope an ensemble system is going to do for you. And this is especially important in the medium range. You're looking at this 1 week forecast stuff. It's critical to have some idea how predictable the patterns are and not just look only at the one deterministic run. Now, the problem with the SREF, at least as it stands, is that we'd say it's not as dispersive as you want it to be, which means every so often, or some fraction of the time, the actual outcome is not included by any of the ensemble members. So something completely outside the envelope of the ensemble ends up being the real outcome. That's not a desirable characteristic of an ensemble. I mean, the idea is you're supposed to be able to corral it and say, hey, the range of possibilities is this, and hopefully the real world outcome will be somewhere between those. It's really bad when here's your range and what really happens is over here. So again, you have to keep in mind, it's not the most robust ensemble, and again, it's been undergoing a lot of changes, so this will impact some of the derived probability stuff that I'll show here in a minute. Okay, the one thing that I know gets tossed around quite a bit. Again, I like to pick on the Facebook shares and all this stuff. I just kind of watch this. And the significant tornado ingredients, this is one of the output fields. This one is actually a joint probability field, which means what we're doing is we're taking all of the ensemble members and we're saying which ones have 500 CAPE. So we're looking at essentially all of the members that have 500 CAPE or greater. And I'll tell you, and we'll talk about why we use these thresholds. And then all the ones with the MLLCL. So you come up with the fraction of the ensemble, and then you multiply all those probabilities. So the idea is to get probability of, say, 90% of meeting all 5 conditions that are listed, where you've got sufficient CAPE, sufficiently low LCL heights, sufficiently strong 0 to 1 SRH, sufficiently strong 0 to 6 bulk shear, and convective precip all co-located. It better be in almost all the members, because again, when you're multiplying the probabilities, it gets much harder to keep high values. So again, we're doing the product of these 5 terms, the probability that each of these conditions are met over the entire ensemble. Now, the threshold values that are chosen here, aside from convective precipitation, that's just to represent, is there any chance of storms? in that particular forecast. Otherwise, we're looking at, if you remember from our parameter distributions, these are roughly 10th percentile type values. Or in the case of LCL, it's the 90th percentile because lower is better. So 90% of the significant tornado events are on the plus side of these thresholds. So it's kind of an estimate of a low-end significant tornado environment in terms of each parameter. So hopefully that makes sense. And that's all this thing is trying to do, is how consistent are we in forecasting a minimal low-end SIGTOR type environment. Okay, so this is the plot. These are the graphics you see thrown around. These are actually, again, the joint probabilities. It's the combination of the probability of each individual one multiplied together. And you can see relatively high values. We contour up in excess of 60, I think, on this. So maybe 75, I think, is the highest contour that we show. But the idea is from Kansas into Missouri and a little bit of northern Oklahoma, as much as half or more of the ensemble meets these conditions, which means it's generating convective precip in this at least sort of favorable environment for supercells with significant tornadoes. Again, it's not a high-end environment. And the other thing you have to remember is convective precip is part of it. You can have a tremendous thermodynamic profile, vertical shear profile, but if you don't have convective precip, which could be related to the convective schemes, it's not going to show up. If too many of the members are dry, it's a great Cape shear profile, but you don't have storms, so it's not going to register on this. So remember, this doesn't necessarily tell you where the best environment is. It tells you where the most consistent environment is for these 5 conditions. Consistent, not necessarily best. All right, and this is just another way, again, we talk about a time lag ensemble. Well, we're going to do a time lag ensemble of an ensemble. So in this case, we're just looking at the change over time, which can be valuable. In this case, it doesn't alter too much, but these are each successive run. And you can look, are there time trends? In this case, you see the probabilities at the end shift back west toward Kansas. It just might mean there's something becoming a little bit more consistent about the environment. It could be, and you have to look at the individual ingredients to know, is it because the models are consistently initiating convection, the schemes are triggering in that area, or is it because the moisture's increased, the shear's increased? It could be any and all of those. And you're not going to be able to tell that from this. Okay, other ways. There are some completely different ways to look at this. When you have an ensemble, you can look at the range of possibilities as opposed to what are the probabilities. We can look at the range of possibilities. In this one, we'll show the fixed layer significant tornado parameter, and I can show this actually instead of you reading the slide. This is just everywhere where the STP, we've got any member is that dashed red outline. Boy, and I didn't do my animation very well on this. Kind of rushed through this afternoon. Any member in the ensemble, so out of all 22 of these, that is the outline of the biggest area that has at least STP greater than 1, greater than or equal to 1. The blue, the inner, much smaller area, that's where every member of the ensemble, all 22 have at least a SIGTOR parameter value of 1. So you can get an idea what the spatial envelope of possibilities looks like with this kind of plot. Where is the predictability the biggest concern? It's in the gradients, the transitions. In this case, as you go west near the Kansas-Oklahoma border. How far west is the more favorable tornado environment going to be? And the question is, where's the triple point going to be in that particular case? And then, of course, we have the median values, which is just sort of the middle. That's the middle value of the SIGTOR parameter for the whole ensemble, done at each grid point, and then just contoured. So values go near 1, 2, and 4, and we have a series of contours in there. So this gives you some idea what the spatial distribution of the environment looks like as opposed to the probability that a bunch of ingredients are going to be co-located. So it's just a different way to look at the same kind of thing. And you can do the same sort of time trends. So we do over multiple runs, how is this changing? So you can see that as we get closer, the area where the SIGTOR parameter is consistent actually expands. So there's more consistency in the model forecast, is all that tells us in the core area, and we're tightening that gradient up. So it's giving you an idea that that favorable environment is starting to tighten up. You know, it probably won't be too much further west of the red line, but it may be a little west of the blue line. So the idea, and that's right where the gradient in the median values shows up. All right, other ways you can look at the environment. We can actually look at the explicit ingredients themselves instead of lumping everything together. And again, you should do this every time. You have to know what the distribution of CAPE, vertical shear, and have an expectation for it. So in this case, this is just a composite spaghetti type plot. You know, we just lump everything in there where we contour and shade the cape in the background and the pinks and yellows. That's ML cape. The wind barbs are the effective bulk wind difference, and the 0 to 3 kilometer SRH is in the hatched green contour. So anything over 200 is that light green hatched area in there. So you can look at how the individual ingredients, we don't have the effective SRH, or we didn't have it coded up, so that calculation's a little bit more complicated, so we just stand with what's already provided to us. So you can look at this and see how the supercell ingredients vary. In this case, if you look at the change over time, you start here, the hatched area, the SRH is actually receding north a little bit toward the Kansas border, but the buoyancy's coming up. So you already see a compensating effect in this ensemble. Whereas you noticed in the SIGTOR distribution, it wasn't the magnitudes weren't changing drastically, but here it's becoming more of a cape-heavy environment as opposed to a shear-heavy environment. So there, you can tell which ingredients are varying in which way, looking at it this way. Now here's the, just since we had a really big photogenic tornado the next day in northern Illinois, here's what the same field looked like valid at 0Z. You guys know it was up there way in extreme north central Illinois, west or northwest of Chicago. It's kind of on the north edge of the worm sector. The shear, modestly strong shear, it's kind of on the north edge of the cape. And remember, this is an ensemble mean, so it smears things a little bit. But when we go to the SIGTOR ingredients, there is a bullseye, probably because even though that environment wasn't necessarily any better in some sense than the way it looked further down in Missouri, there's a much more consistent convective precip signal. So we're more confident that there will be storms in that environment, and so there is actually a little bullseye in northern Illinois. And by the same token, it's a relatively consistent environment, at least for this lower threshold SIGTOR value of 1. So this is one way the ensemble stuff could help you, maybe focus your attention. But again, we have a whole bunch of other fields on there. You can look at higher values. There's all sorts of other stuff that I encourage you to explore. These are just sort of examples of 3 or 4 different basic ways to look at the information. All right, so again, we have some other stuff. If you look on there, there's a tab for the calibrated or SPC severe stuff, generated stuff. Over the years, we've used these SREF forecasts. We build up a big archive, and we look at, say, okay, different combinations of cape shear, and say, what happens when there's lightning? What is actually happening in terms of severe weather? And so we just build up this big sample, and then we can go back and say, okay, if we have this cape, this range of shear with convective precip, what fraction of the time is there a severe weather report within some distance of that grid point? And so we can actually come up with a calibrated means of estimating the severe weather threat from the background SREF forecast. Now, one thing I want to caution you on is the SREF has been in flux, and I was more confident in this information 2 years ago than I am now. It does not look like it has been left alone for very long, so that we have trouble building a big statistical sample. We need tens of thousands, if not hundreds of thousands of cases to build this up and get robust statistics. And every time the SREF changes, we have to start over. So there's a big spin-up time. So we really need it to sit relatively stable for a year or two to get this stuff to work. So it's been a little bit erratic, but here's what it looks like. These are actually SPC outlook style probabilities. In terms of the values, you notice the peak of the scale is 15. That would be loosely equivalent to like our 15 hail, wind, or tornado outlook probability. So what this does is this says over a 3-hour period, what's the probability of a severe storm based on the various bins of cape shear, convective precip, and a few other parameters, and it's a little more complicated than that. And you see there are bullseye type structures in there. There's higher probs in Missouri and then toward the Kansas-Oklahoma border. Again, time-lagged ensemble, a poor man's approach. Look at the consistency of these type forecasts. And you notice that as you get closer to an event, frequently these probabilities go up because the uncertainty in the location of boundaries diminishes typically. The focus for convective initiation improves, and the consistency in the background ingredients improves. So, you can get something from this, and oftentimes the nice part about this is it can highlight areas that you weren't necessarily thinking about. If you're responsible for a national convective outlook, this is a good safety net, this kind of product, because it's looking everywhere all the time. So if I don't remember the details, but you look up toward the Nebraska Panhandle, there might actually be something sneaky going on there. I don't recall in this case what actually, if anything, happened. But it might get you to look and say, what is going on there that I might have overlooked? And then if you're trying to outlook high probabilities and this looks rather subdued, you might ask yourself, okay, am I overdoing it? So it's a way to help us calibrate our outlooks. Okay, this is what happened that day, just to show you, you look at that corridor of the higher probabilities, Kansas, Oklahoma, across to Ohio. Indeed, the severe weather events tended to occur along that same corridor. So and this is one of these things that as we build a bigger sample, the calibration gets better, and the reliability of these forecasts gets better. And then just for sake of completeness, we'll show the next day. Here's the little highest probabilities locally and up there in northern Illinois. But you notice there's similar probabilities all the way into northeast Texas. Same thing when we looked at the tornado ingredients. It doesn't mean that there will be, the weather's going to follow this exactly, but the idea is that generally within that swath, and this is just a 3-hour portion of it, the severe weather events are scattered through there, but indeed there were other areas besides northern Illinois. And that's the challenge at SBC. I'm not looking just at northern Illinois. Coworkers, we've got to get this entire swath right, and that's not always the easiest thing to do. Okay, Nessel from the WRF ARW produces what we call surrogate severe probabilities. This is a kind of a smooth version, and it's meant to look like our outlook probabilities. And we call it this practically perfect. It's the idea of if I gave you a map of reports and said, okay, you can't just click on the counties that have all the reports. That's cheating. But if you were to draw kind of a smooth area that represents where these events occurred, that would be the best. You're practically perfect, the best you could be expected to do in any real-time forecast scenario with lead time. So what it does is it's just a way to spatially smooth the influence of reports and come up with something that would be a pretty darn good forecast if you were to put that out in advance. Okay, so here's what it looks like. This is using all sorts of things from the Nessel forecast system, updraft helicity tracks. They have some other estimates of hail production and wind and all sorts of things. And this shows, you've seen the report distribution. This shows what's the probability on kind of a smooth grid of severe weather somewhere in the vicinity. So these probabilities get pretty high, 70%. So it's saying that severe weather is likely from northern Illinois down into northern Arkansas. And the severe reports, if we go back, just so you can see it, it helps if I actually go back. There we go. So there were reports through there. It's not that it's a perfect alignment, but remember, that's derived from just a single forecast. So it's actually pretty good. From one forecast, you can get that. And of course, we can look at the probability that updraft helicity over a certain threshold, in this case 25 meters squared per second squared, is exceeded. Notice it doesn't highlight northern Illinois particularly well in this run. It's more down toward Arkansas. So again, this stuff is not perfect, but it is useful guidance. Okay, the SSEO, our poor man's ensemble of the available CAMs. This is the Nessel WRF, some of the NMM runs, the so-called SPC run that you see on the MC site. Again, it's not a classic ensemble because nobody's designing it to be that, but they're different models, different physics, different initial conditions. So in a sense, there's a lot of diversity in the ensemble by accident because it's basically all the CAMs you can normally find. And the good thing about this is we grab this information, somebody in the background had the good idea to make an ensemble out of this, and there's actually some pretty neat stuff you can derive from it. Okay, so I'm going to focus on the UH, the updraft helicity at multiple thresholds. You can look at these so-called spaghetti plots where you just plop them all on there, or you can look at probability. It's derived from the ensemble, and there's a whole bunch of other stuff. You can look at reflectivity, you can look at 10-meter wind speeds, all sorts of stuff like that. So the idea here is this is a forecast of maximum updraft helicity during the forecast run from all of the ensemble members. There's 5 or 6 of them that are in here. And you can see individual tracks. You can actually see how different models handle the supercell tracks a little differently. Some of them are oriented slightly different than others. This is just where the strongest winds, the highest values for that grid point win. And so you see all sorts of little worm trails that are different storms. It looks like at least one of them had a much more intense rotating storm in eastern Kansas. And you can see where they're clustered. And the idea is we can use this clustering and come up with probability stuff. Well, here's the very next run available. Again, 12 hours later. There's some similarities. We have the corridors pretty similar, but now we're not so much emphasis in Kansas. Some of that's shifted south. Now there's this big emphasis around St. Louis. So, you have to sort this out. Does this really mean there's going to be a cluster of supercells around St. Louis and they're going to be intense supercells, or is this a quirk of the one or two particular model solutions? Now, if you combine these, we can actually do what's the probability in neighborhood sense, like within some distance of an area, that we get updraft helicity over a threshold. These are pretty high values, 70, 80%. So this says there's a nice corridor where it looks like supercell storms are probable based on the ensemble. Later, the probabilities come up as we get closer, we resolve the event. And again, this is anywhere in the 24-hour period. We also have 3-hour time windows. I'm just not showing that for the sake of brevity. Conversely, you can look, will there be intense supercells? Let's take a much higher threshold for updraft helicity, 100 in this case. Notice a lot fewer storms are rotating that strongly. So this says there's a lot of supercell potential, but I don't know, it's not obvious that they're going to be really intense storms, except for the little bullseye around St. Louis. And so the question is that real? But it tells you the whole swath doesn't necessarily look like they're the most intense storms. And here's a way to summarize that stuff. This is something we produced in the background. Those contours are probability, sort of a practically perfect version of the updraft helicity of 25. So where's their organized storm potential? We draw the envelope and then overlay the reports on it. So the idea is you can see that where, in a collective sense, the organized storms are forecast to be matches up pretty well with the report stuff. And we have this guidance available. I get this in email every morning, so it's generated internally, and that's another way that we use this information. Okay, now here's just, again, we'll look at I've shown you some of the stuff from the Illinois case, the Rochelle, Fairdale tornado, whatever it was. Here's one of the one that was furthest out. This is essentially you could argue about the 24-hour forecast. There is one intense updraft helicity track up in the vicinity in that run, but not a whole bunch of storms. So there's like one run has an intense storm, but there's not real consistency. It looks more consistent down south. The later run, the UH tracks aren't as strong, but there's a lot more of them. So you have some intensity, consistency concerns looking at this, and when you put it in terms of probabilities, again, it looks like the probability of rotating storms is much higher down south, but when you look at the end, there's a little more consistency, though it does come up in time. But the probability of an intensely rotating storm really isn't any worse up north. So again, you have to weigh this evidence, and it helps to be familiar with interpreting this stuff. But it's something, if you don't start looking at it, you won't know how to use it in the future. And again, there's the same plot I showed before, just applied to the next day. Again, you see pretty strong correlation spatially between the area where updraft helicity probabilities are high that there will be at least weak updraft helicity, and where the events are. Now again, this kind of guidance can fail if you don't have rotating storms that are producing it, but since this is a spring case and a lot of these were supercells, it works pretty well. All right, other stuff you can use. There's analog forecasting. This is the so-called SIPS analogs. This is from St. Louis University. You've got the link there, and all this is doing is trying to pattern match. It says, okay, what does the forecast look like, and how can I use I think it's the North American reanalysis data, to go back and pattern match and say, looking at the distribution of heights and temperatures and winds and that sort of stuff, to say what patterns looked like this in the past data, and then what happened when those patterns with those occurrences. So, and then they do some smoothing, much like the Nessel ARW, that practically perfect. They come up with work backwards from the event and say, okay, here's what an outlook could have looked like. All right, so what they start with is this is a case from again, this was the other day, the April 9th event. These are all the severe weather reports with the top 15 analog matches for that forecast pattern. So this is all of them. So again, this isn't one event. This is 15 events all piled on top of each other. So if we take out, since we're interested in the tornado part, this is what all the tornado events look like for the analogs for that particular forecast. The little black ones, triangles with the lines, those are the longer track, more significant tornadoes, whereas the red triangles are just the essentially brief short track tornadoes. So you can see there were quite a few tornadoes. Again, this is 15 events, so it's not an enormous number. It doesn't tend to be centered over northern Illinois, though. It's more to the south or west of there. So something you can look at. Other things you can do from this is with the top 15, they say, okay, what fraction of them? In this case, I'm just showing the percent of those analogs that had at least 10 or more reports. So strong clusters of reports in the scenario. And there is sort of a tendency for more of the analogs to focus somewhere up toward northern Illinois. But again, it's only 20% of them. So there's pretty strong clustering of the reports in 20% of the ensemble, but that means a lot of it, the other 80%, it wasn't necessarily that strongly clustered. Here's the SIGTOR analogs. Again, the probabilities, these are SPC style, outlook style probabilities, so they're meant to work about the same way. This is a much smaller area. There's a weaker signal, and this is just, again, the probability of at least one SIGTOR. So it doesn't jump out at you. You see stronger signals than this. You can lump, now what they do is they also look at the top 8 analogs. So we'd say the 8 closest matches. Instead of 15, let's take the 8 closest matches, do a practically perfect forecast, and then in this case you get probabilities that would be equivalent to like the day 2 outlooks, total severe. So in this case you see 30s, northwest Illinois, and another corridor back into eastern Kansas. You can do tornadoes, and these are color-coded the same way as the SPC outlooks. That's the 5 TOR, so that's what its analog tornado outlook would look like compared to what SPC did, which SPC had higher tornado probabilities. We had a 10 SIG area, I believe, was added in northern Illinois during the day. Okay, there's one last thing. Well, I promised I wouldn't spend too much time on it, but this one, it's just funny enough. I don't know if you guys can even see this stuff when I show it, but I don't remember if it's publicly available, but it's rather amusing, forecasts out to 6 weeks and that kind of stuff. And it's rather depressing when you see the forecast. This was the most recent run from last night. Again, if you insist on making a 1 to 6 week forecast, there's information out there, but the question is, how useful is it? Okay, this takes a little bit of time to get oriented to. The x-axis and the y-axis both span 6 weeks. They're just scaled a little bit differently. And what we're doing in this particular plot, it's affectionately known as the chiclet chart. I guess because these are supposed to look like chiclets, the gum, if you guys even know what that is. But different colors, it looks like a bunch of those little square gum things stacked against each other. This is essentially like a grid count of the supercell composite with convective precip. And the CFS system has 4 members that run as a sort of a small ensemble. And all those squiggly lines in that upper right inset, that just tells you the range of number of grids per day, 24 hours that have, if it's higher up the scale, there's bigger areas with presumably a supercell favorable environment with convective precip. And I'll show some examples of what the individual forecasts look like. But if you look here, so this is time, the forecast or going backwards from now is going down the diagram. So that would be where the purple line is 1 week in. So we're only looking 1 week back, and you notice then go 2 weeks back. Now I'll highlight this little signal right here. That's the 7th to 9th of April severe weather episode, the multi-day thing. That's what it looks like in this term. There was a concentration of environments with bigger areas with supercell composite greater than or equal to 1 with convective precip. So it's just a proxy for an organized storm environment. Now you notice a lot of the rest of this. Remember, this goes back 6 weeks. It goes way out in time. What do the blue colors mean? Not a whole lot. You can see our slow winter and spring. Look at that. Dark blue means almost nothing. Anywhere in the CONUS is what this is adding up. When you get a good forecast signal, you'll see these vertical spikes like this. So this goes back at least almost 2 weeks in advance. You can see some signal within a few day range of relatively high values. Now look forward, which is going to the right at the top of the diagram. That's the CFS forecast all the way into late May. What do you see? Sad. Notice there's no consistency. We don't see any strong signal. So what this suggests is, at least in this modeling system, this is not very suggestive of large-scale troughs with big, unstable, warm sectors and convection. That's not what's showing up in the ensemble. There's only one signal. So this is in a 6 week period. There's only one single signal like that. And that's why this is the only event we've been talking about, is because we don't really have anything else to focus on. So the point here is that it doesn't look real exciting in the future, and I know I'm not supposed to be doing this extended forecast stuff, but that's April 21st. That's next week's, it's supposed to be the last session here where we do a real-time forecast. Dark blue. If you look at most of the medium range guidance, there's a trough sitting in the east and there's a front somewhere in the Bay of Campeche off the Florida coast and the Atlantic coast. That's not exactly a primo setup for severe storms, well, anywhere in North America. So the point is, what we're going to try to do is push it to the next week. Now notice it's still dark blue the next week. However, that's at least getting to where predictability is not as good. Notice where the warm colors showed up on that. It was only just over 2 weeks out that signal really even showed up. Because if you go down, that's going further out in time. It's dark blue. It didn't resolve that scenario until we got within about a week and a half, 2 weeks of it. So what I'm hoping is that maybe if we push our real-time forecast exercise to sometime the last week of April, 28th to the 1st, maybe, just maybe, we can get an event with at least some interest to you guys, and we'll try to do a forecast. If it's anything local, what I'll promise to try to do is we'll do it the evening before, not the day of. We'll do the evening before, and I think this is during dead week, but the idea is maybe blow off some steam, and you'll probably be sneaking a peek at the weather anyway, so we'll just kind of treat it like a big map discussion and do a forecast collectively. So that's kind of what we're looking for, and this is just one of many tools you can use. Again, here's what the individual events look like. This is a 24-hour forecast from that system. The blue area is the convective precip, and then the contours are the supercell composite, and then you see the reports overlaid. And this isn't a terrible forecast. That's 1 week in advance what it looked like. So it's, there's not wild variability. This is why you saw the predictability in this setup, because literally it didn't vary greatly over a week. Okay, well then, as I said, we'll do the forecast stuff. I don't know if it'll be fun or not, but I've used that one before, that tornado forecasting is easy. If you're right, it's easy. But we'll try to do that, but just sort of if you want to be part of that, we'll try to announce it at least a couple days in advance. Depends on what we can scrape up. And who knows, if it looks terrible, maybe we'll just reschedule to another time. There's nothing that says we have to do it right now. But the idea is I'd like, while it's still fresh, to tie all this stuff together and show you how I would go about making a forecast while you can ask questions and essentially apply all this information that we've been going over and show you that we actually do try to use this in real time. So that's all I've got. This is the end of the regular session. So again, we'll get the forecast one in when we can. Appreciate everyone coming, and that's all I've got. I am tapped out.